Good afternoon, my friends and viewers at home, and every one of you, wherever you are watching me around the world, like in the office, in your homes, and wherever you are. Just as we promised, we're going to be talking about strictly on questions and calculations that involve in electron potential, which is, I believe that before you start watching this video, you've watched my previous clip because it's going to help you on this aspect a lot. Now, a question was given to us, example one, giving you the half cell reaction of various metals that are here and their standard electron potential. The question now says from the above data, it can be deduced that the most powerful reducing agent of the four melter is. Now, simple. Now, how do we analyze such a question? Very simple. Now, remember in our previous video that we did, I said categorically that if I'm having two species, let's say A and B, and that A is positive, B is negative, I said that it is the most powerful, that the most positive is what now? Is the ovidant, while the most negative is the redundant. So it simply means that from what you're having here, copper, which is an ovidant species, will not be part of the option. So it now lies between iron, barium, and zinc because they are negative. But don't forget, as I told you in the previous video, that the most negative is the most powerful reducing agent. Now, if you check all of them here, the element or the species that is most negative here is barium, having a standard electron potential of minus 2.90 volts. And as such, the answer just popped up like that. So the answer is C. So move to the next question. Now we solve example 2. But before we solve example 2, there are some basic things that you should understand or realize. And that is basically the formula for EMF, which the electron potentials can make us to know or be able to solve. That the EMF of a cell or the electron potential of a cell is equal to the electron potential standard of the ovidant minus the electron potential standard of the redundant. But you should understand what when we say that a reaction is feasible and that a reaction is not feasible, and knowing when to make use of this formula and when to make use of the opposite, which is the standard electron potential, which is equal to the standard electron potential of the redundant minus the standard electron potential of the ovidant. See, I've turned it now. Now, we make use of this formula when the reaction is feasible. And when we say feasible, it simply means that it's possible. Not only that, it also means that the cell notation, or we make it of it when the cell notation is not given to us for the question. So it means that if the cell notation is given to us in the question, it will be not feasible. But if not, it will be feasible. That is when we make use of this formula that you are seeing here, and which very simple. I can also say for this formula that the standard electron potential is equal to the reduction minus the oxidation. And it's very simple. Now, how do we solve such a question? The question says, what is EMF and cell notation of a cell containing what you are seeing here, zinc 2 ion interface zinc and copper 2 ion interface copper electrodes. If the electrode potential of this and this are minus 0.673 volt and plus 0.33 volt respectively, it's very simple. Now what do? We'll use two methods in solving this question. We'll make use of the formula method and also make use of the direct method, which is simple. Now, here becomes E naught of the cell is equal to the E naught of the ovidant minus the E naught of the redundant. Now, if you check this question very well, you see that the cell notation was not given to us from the question. So it means that the that this reaction, that this process here is feasible. So, and if it's feasible, make it of this formula. Now, we determine the ovidant and the redundant. Now, what is the ovidant from this case, and what is the redundant? And I've told you that when you are given two potential difference, which is one is negative and one is positive, I've told you that the ovidant will be the positive, which is plus 0.337 volts, while the redundant will be the most negative, which is what now? Minus 0.763 volt. From here, your answer comes out, and the answer becomes E naught of the cell is equal to the ovidant here is 0.337 minus bracket minus 0.673 close bracket. When you do everything here, what you should get at the answer should be 1.10 volt. That is it. Now, remember, they've told you that what is the EMF of the cell and the cell notation. Now, to know the cell notation, very, very simple. How? You are aware that for a thing to undergo ovidant, it means that this one is reduction. And for a thing to undergo redundant, it means that this one is what now? Oxidation. So it simply means that you are aware that the cell notation is equal to oxidation slash the reduction, and as such here now becomes for the oxidation here now, so is this one, and which is that of the zinc, and for oxidation it means that there's an increase in oxidation number. Simply tell you that you have to turn this one, which is zinc interface zinc 2 and zinc ion, the interface, then that of the copper, so the copper 2 ion interface copper. So that gives us the final answer to this question. But this is method 1. For the method 2, which is the direct method, which is the one that we mostly make use of, that with this method there tend not to be error in our calculation, is very simple. So what do we do, or how do we go about it? You simply, since you now know that your ovidant is this and your redundant is this, very simple. Now we move ahead here. So for the reduction, which is that of the copper, reduction, which is that of the copper 2 ion, that as we have here is, which is Cu2 plus will give me copper, and the electron potential gave me 0.337. This is for the electron potential. Now for that of the oxidation, remember that whatever, for example, if I'm having A to give me B, and I'm having here to be, let's say minus 2.0 volt. If I should not say B to A, the sign will also change to give me plus 2.0 volt. So it's telling me that since I'm having zinc 2 ion interface zinc, I'm having minus 0.673. If I should not change it to not have zinc to zinc ion, it means that this minus sign will change to what, and plus to give me 0.673, which where to balance the electron here. For reduction, electrons are added to the left hand side, and for oxidation electrons are added to the right hand side. So with everything here, the answer still remain 1.10 watt volt, which is similar to what we have just done here. All right, we move to the next question. So we move to the next questions. I said, given that the E naught, which is zinc 2, and the zinc ion as interphasing to give us this volt, and silver ion uh, and silver metal to give us this volt, to calculate the standard cell potential of the cell. Now, very simple. Now, if you look at this question now, this question we're giving the cell notation. So that's a guide. It sees the cell notation as beginning to run. Now, I would have said let us make it of the other with the formula that says E naught is equal to the E naught ordinate, the E naught ordinate minus the E naught redundant. But the reason why using that formula now will be a little bit confusing is that we need to know whether this, since we're giving the cell notation, we need to know whether the reaction is feasible or not. But I'll give you, not to waste time, we'll just do the direct method so that we'll just save time and understand it. Now, so the direct method very simple. Since you are giving your cell notation, just work on it. That's all you need. And you already know that your zinc interface zinc ion, which is zinc to zinc ion, that this one is what now? Oxidation. Now, and if you look at what we're giving here, we're giving so since we know that sorry for the break in transmission, so we continue. Now, since I know that from zinc to zinc ion is oxidation, and we're giving from zinc ion to zinc to negative 0.76 volt. So it means that we need to change this negative sign to positive because of its now oxidation. So that becomes plus 0.76 volt. And that, yeah, from zinc ion to zinc, from silver ion to silver, since it's reduction and we already have it in the same reduction, so we just put it to the plus 0.80 volt. Remember, if you balance it for oxidation, electrons are added to the right hand side, while for reduction, electrons are added to the left hand side. So, and as such, we'll do it like this. We just have to add it up to the 0.76 plus 0.80, and the final answer is 1.56 volt. That is the final answer. So move to the next question quickly. The next method is very simple. The next question is very simple. So we'll just move straight to the calculation, not to waste time. We make it of the direct method. But if I want to make it of the formula method, it's also possible. But I will prefer the direct method, not to waste time. Now, what do? We come back to say, since you're giving your cell notation, just think of your cell notation. You get me now? But if your cell notation is not given to you, that's when you make it of that formula. The first one we use to solve the question. But if it has a cell notation, simple, you should not just bother to waste time on it. Just move straight. Just move straight to the direct method, which says from Fe to Fe2 plus. This is oxidation, which is written first. Then reduction, which is zinc 2 to zinc ion, which is zinc ion to zinc. Now, this one is plus 2e minus at the same time, and then it plus 2e minus. So it's simple. Now, for this is for oxidation, which is from E to, so it means that we have to now turn this one, because here it was Fe2 plus to Fe. So and here is Fe to Fe2 plus. So we have to now turn this one to become Fe to Fe2 plus. So here becomes the electrical potential here becomes minus 0.44 volt. Why that of the zinc ion to zinc matches with this one that we're giving for the electrode potential, which is the standard. So here becomes the same thing as minus 0.76 volt. or nothing was turned. So we just come here and the answer will give me minus 0.32 volt. That is how easy. That is how easy it is. Now, in our next video, we'll talk strictly on next equation. Please, for any question that you want to ask, feel free to send your questions to my number, which is 09081053321. Right on the board, 09081053321. This is my WhatsApp line in case you want to WhatsApp me for any question. So God bless you. God bless you.